So in this video, let's discuss the topic Rutherford's theory of alpha particle scattering. So let's have a look at this. So we would have we can see complete theory along with the formula derivation here. So first of all, alpha particles are highly energetic, positively charged particles emitted by radioactive substances, and the amount of the positive charge equal to units of electronic charge. So we know that alpha particle is nothing but doubly ionized helium atom. That is, if we remove two electrons, if two electrons are removed from the helium atom, that is He2 plus, that is nothing but alpha particle. So in helium atom we would have its atomic number is 2. So 2 protons and 2 electrons, again with some combination of neutrons also, along with protons we could have some sort of isotopes like that. So that's another thing. So in the nucleus we could find protons and neutrons, some finite number of neutrons depending upon the isotope, and electrons. So from the, if we remove electrons, the remnant, that is nothing but nucleus. So that is nothing but doubly ionized helium atom. So that is nothing but alpha particle. So as we know that atoms are neutral, and on removing two electrons from the helium atom, so initially its charge is 0 because it is a neutral, 2 protons and 2 electrons. But now we have as we have removed 2 electrons, so now it is positively charged, that means plus 2. So that's why highly energetic positively charged particles. So it is positively charged, but they are saying it is highly energetic. So how they are getting its energy? So why they are getting that energy is because of emission by radioactive substances. So when the radioactive nucleus decomposes, undergoes fission, nuclear fission reaction. So in such a process we could find these alpha particles. So the initially the nuclei might be at rest. So after the fission process, so a parent and that are the two different whatever we are getting. So this huge nucleus would be splitted up into actually. So this huge nucleus would be splitted up into some other form of nuclei of smaller size and along with alpha particle like that. So in such a process, it is emitted with a huge kinetic energy, those alpha particles. So hence they are highly energetic in that process, while in the process of decaying of those atoms. So radioactive substances, when they get decayed, and their mass is equal to that of helium atom. So nearly it is equal to that of helium atom, because electrons mass is considered as negligible. So they are emitted during radioactive disintegration. Thus we have discussed now this uranium radium because of this disintegration, that is nuclear fission reaction. So when a unstable nucleus it decomposes into different atoms, that is nothing but nuclear fission reaction. That is heavier nuclei, when heavier nuclei decomposes into smaller nuclei. So that is nothing but nuclear fission reaction in that process. When the mono energetic, so next thing is, now when the mono energetic alpha particles emitted from a radioactive substances are allowed to pass through a very thin metallic foil, that is metal foil, they are found to scatter in different direction with respect to direction of emitted beam of incident particles. So now what we need to do is, so some decaying nuclei, this is a source of alpha particles, some uranium or some radium like that. So from it would be releasing its own alpha particles. So here they are saying mono energetic alpha particles emitted. So we have to take single energetic, that means alpha particles of a particular energy. That means it might be some 10 million electron volts or 20 million electron volts, something like that. So but it has to be have of mono energetic. not varying from 10 to 15 or 10 to 20 like that, but a particular energetic. So of course can be here and there between some it may some nearly 9.999 10 10.12 10.11 it might be having. So but here for a complete understanding we are sending mono energetic uh, alpha particles. So why means let us see. So it would be emitting alpha particles. So here we are keeping some thin metallic file. It has to be thin. If it is thick means uh, so if it is very very thick means fat means what happens is alpha particles would lose their energies to many nuclei present. So if it is very thick means many nuclei would be present, and they would lose their energy in the halfway. So we can't study properly what's happening inside the atom, like that, inside that nucleus what's happening. So if it is very thin means okay, so some limited number of nuclei would be present in the way, so they would not lose, alpha particles would not lose their energy easily, and we can study them how much their energy is getting reduced, like that. So that's why. And so though by far great so here it is mentioned great majority of the alpha particles are scattered at smaller angles, and a small fraction is scattered at large angles. So most of the alpha particles are scattered at the smaller angles. So very very small angles they are scattered, scattering. So if this is the direction of incident alpha particles, so actually they are going in this direction, but after moving to the metallic file they may move in these different directions. So this is incident direction and this is deflected direction. So the angle between that is nothing but angle of scattering. So some might be scattered at lower angles like this, just as small angle, and some might be scattered at the large angles like this, or like this, or even 180 degrees like that. So like, so if this is the incident direction, some of the alpha particles would be scattered at smaller angles in this direction, some at larger angles like this, like this. Some might be returning back, that is 180 degrees. So they are saying most of the alpha particles are scattered at smaller angles like this, and very few are scattered at the larger angles. So this is very important point to be noted. So this helps us to study a lot about the structure of the atom. And why it is so, we will see further. Such large angle scattering cannot be explained on the basis of Thomson model of atoms. So Thomson, J.J. Thomson has proposed a watermelon model. So it's just like a watermelon, seeds embedded on the watermelon is nothing but electrons, and that flesh is nothing but protons. So it is just electrons in a sea of photons. In such a manner the atom is distributed. So electrons, if this is some atom, so here photons, everywhere photons would be present, and in the between seeds, just like the seeds, electrons would be present here and there, like that. So uh, so this could not be explained by this model. So why it is scattering in such a manner? So we could not take, so at that time, so J.J. Thomson's model was looked weird to explain the structure of atoms by this experiment. So a new explanation is required. So that one we will see. The reason for which is understood qualitatively as follows: the electrostatic repulsive force between positive charge of the scattering atom and the alpha particle. So so this is the alpha particle and this is the scattering atom, that is scattering nuclei. So as we know, atom has got positive charge as well as the negative charge. So the force between the positive charge of the scattering atom and the alpha particle inversely upon square of the distance of the alpha particle from the center of the latter, and directly proportional to the positive charge of the scattering atom. So we know that from Coulomb's law, force between two charges is nothing but 1 by 4 pi epsilon naught q1 q2 by r square. So it's q1 q2 by r square like this. So from this we can see that the repulsive force between repulsive force or attractive force between two charges is directly proportional to the charges. So F is directly proportional to the charges and it is inversely proportional to the distance between them. So F is inversely proportional to the distance between them. So that is, it has been explained over here. So that is the meaning of this. So it's just a simple thing. So not much explanation is required for this. So next is directly upon the portion of positive charge of the atom. As we shall see, the angle of scattering increases with increasing effective charge of the atom. So that is, as the effective charge of the atom increases, that means the charge which is showing effect on the alpha particle. So more is the charge, more is the repulsion, like that. The repelling the alpha particle. Angle of scattering increases with increasing effective charge of the atom repelling the alpha particle and decreases with increasing distance from the center of the particle passes by. So when the particle passes through the atom at a relatively large distance from the center of the atom, so the angle of scattering is quite small. So if this is suppose this is atom and this is alpha particle and this is alpha particle, so it is uh, let us take two alpha particles. So this is one alpha particle and this is another alpha particle. So this alpha particle is very far away from this atom and this is somewhat nearer to this atom. So this alpha particle experiences less repulsive force. So it deflects a little bit. So that is the meaning of this. The distance becomes so large that the angle of scattering is quite small. So its effect is very less because the distance between the atom, that is the positive charge, the atom is nothing but the nucleus and electrons, that positive charge would be showing effect on this alpha particle. So that is nothing but, so the angle of scattering is quite small because effect is less, because force is inversely proportional to the distance, even though the entire positive charge of the atom repels it. So even overall this entire positive charge, even though this entire positive charge repels this atom, so it is deflection is less. So here you can see for this alpha particle its deflection is less. And next thing is, on the other hand, on the other hand, the alpha particle passes by a relatively close distance from the center of the atom. The effective charge repelling is so small that the angle of scattering is quite small again. So this alpha particle, you can see it is moving still more nearer to the atom, but the effective charge repelling it is very less. That is, only this much is repelling, it might be repelling it. So this, its effect would be negligible because it is very far away, because it is this alpha particle is uh, nearly going towards this, so its effect would be more. But this alpha particle is going here, so entire charges effect would be more. And so that's why effective charge for this alpha particle is less. So here in this we are having two scenarios. So for this alpha particle it is at a larger distance, here distance is greater, and that's why scattering is less. That is, for this alpha particle distance is greater, so scattering is less. And for this alpha particle effective charge q effective is less, so very less. So that's why here also scattering angle is less. So that's the meaning of it. And next thing is, to explain the above observed angle of scattering, Rutherford. So To explain this all these things, Rutherford proposed the model finally. So according to him, the entire positive charge of the atom and almost its entire mass are contained within a very small sphere near the center. So this is very important conclusion we have gotten from this alpha particle scattering experiment. This positively charged heavy core is known as atomic nucleus. So when alpha particle passes by very close to the center of the atom, it feels a strong electrostatic repulsive force due to the entire positive charge of the atom. Hence, it is scattered at a relatively large angle. So, but J.J. Thomson said what is so in the sea of photons. So if this is a photons, so there would be electrons here and there. So here, just like the seeds embedded. So this is the atom. But according to Rutherford, nucleus is located exactly at the center, positive charge, and electrons would be revolving around it. So electrons would be moving around it like this, like this. So 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 from you can see a huge difference between this model and this model. So here photons are nothing but C and electrons embedded there, but here the uh, nucleus is exactly present in the middle. It is the entire positive charge is concentrated at the center, and only the electrons are remaining at the outer layer. So the here the photons and electrons both are separate. There is a large distance between them both. So that's why. So and we know that alpha particle is a positively charged particle. So here these photons are positively charged, that is nucleus, protons and neutrons. So overall, of course, neutrons aren't having any charge, but protons are having charge, that is positive charge, hence the nucleus is positive. So these alpha particles are also positively charged, so they should get repelled. So here you can see, so this alpha particle and this alpha particle are very far away from this atom, so their deflection is negligible. But when an alpha particle goes nearly here, so it's sometimes it may get deflected back 180 degrees, or sometimes it may get scattered at the larger angles like this. So larger angles means you need to understand. So larger angles, like instead of going like this, it would get deflected like this. So here you can see angle of scattering. So here this is incident angle and this is scattered ray. This is the incident direction of the alpha particle, this is scattered direction of the alpha particle. So the angle between them both is very large. So let us clearly understand this angle of scattering. So suppose this is the nucleus. So if suppose alpha particle is going in this direction, so and it gets scattered in this direction. So here this is the incident direction and this is the scattered direction. So here the angle between them both, so this is nothing but angle, this is angle of scattering. So here it is very less. And another case is like the same way. Let us see another case. Suppose the alpha particle is going in this direction and it gets scattered in this direction. So again if we, so here this is the incident direction and this is the scattered direction, this blue color one, and the angle between them is very large. So this is nothing but angle of scattering. The angle between incident direction of the alpha particle and the scattered direction of the alpha particle, that is nothing but angle of scattering. This entire concept is based on this angle of scattering. If we could understand what is this angle of scattering, then we could understand this entire thing easily. So the here very basic thing we need to understand is angle of scattering. So the angle between in the incident direction of the alpha particle and the scattered direction of the alpha particle. So alpha particle is incident in this direction and gets scattered in this direction. So the angle between them both. So it is getting incident in this direction and it is getting scattered in this direction. So the angle between them both. So it is getting incident in this direction and it is getting scattered in this direction. That means exactly opposite, 180 degrees. So understanding angle of scattering is very important in this alpha ray scattering experiment. So that's the thing. So what he have found is by this it was concluded that positive charge is almost contained in a very small sphere at the center. So that is the conclusion drawn from this experiment, because only a few particles, suppose this is an atom, most of the alpha particles are getting scattered at the lower angles, because if this is entire atom means, so let us suppose, so this is the nucleus of the atom and this is the electrons surrounding. So this is the entire atom. So entire atom is nothing but the empty space. Most of the atom is nothing but empty space. So here only some of the electrons are a very large distance between nucleus and electrons. So entire mass is concentrated over here. So most of the alpha particles. So most of the alpha particles are scattered at lower angles. They are scattered at lower angles, but only a few are scattered at the higher angles, because only a small space is occupied by this positive charge, not the entire atom, just as in J.J. Thomson's model. So likewise, so that's why only a few particles are getting scattered. So in only a few particles are getting scattered at higher angles, and all of them, most of them are going undeflected, most probably, because the entire atom is nothing but empty space. So because of that only we have got this conclusion from the experiment, this kind of observation from the experiment. So that is the thing. And so let us see how this experiment is conducted. So during the scattering experiment, a narrow collimated beam, collimated means parallel. So beam of a monoenergetic. So it has to be of single energy. So if it is of single energy, then only we could understand. So how a single energetic alpha particle is getting scattered in different direction. If it is of different energies means we could get a weird result. But we want for a single uh, kind of energetic particle, how it is getting scattered. That means if this is an atom, so we are sending the same energetic alpha particle in this direction, in this direction, in this direction, we are observing. So how it is getting, it is of equal energies, we are sending them, all of them with equal energies, to see how they are getting deflected. So that is very important. So monoenergetic, the term monoenergetic is very important. Is allowed to fall on a very thin foil of metal, so that metal is nothing but gold or silver. So anything we have taken, but it has to be of thin foil, it has to be very thin. If it is thick means we would have many atoms. So if it is thick like this means the alpha particles need to pass through many nuclei. If it is thin means some nuclei, so it would lose less energy, and we could observe the outcoming alpha particles, and we can make a clear observations on them. So that's why it has to be very thin. And next thing is so these metals could be beaten to a thickness of 0.1 micron. So we know that 1 micrometer is 10 to the power of minus 6 meters. So based on that, so 10 to the power of minus 7 is nothing but 10 to the power of minus 1 into 10 to the power of minus 6. That is nothing but micron. So 10 to the power of minus 1, 0.1 micron. So like that. The alpha particles do not lose any appreciable energy passing through thin foils. So that's why we need to use thin foils. Arrangements are provided to count the number of particles in different directions. Force experiment. So the schematic diagram. So here you can see, you could see the diagram. So this is the source of the alpha particle. So it can be uranium, radium, any radioactive element which emits alpha particle. And this is the foil, metallic foil. So they come with energy and they fall on this foil. and finally they would get scattered at different angles. So for observing those particles, we have fixed here microscope with fluorescent screen. So when fluorescent screen, sorry. So when the alpha particles falls on that, we could find the through the scintillations we can count. So this microscope would be moving, and it would be finding in which direction the alpha particles are scattered a lot. In this or this, in whether it is this direction or this direction or this direction, like that it would be seeing. And the force experienced by the alpha particle is a central force varying universally as well. So it is a central force. F is goes to k into q1 q2 by r square. So electrostatic force is nothing but a central force. It is known from the laws of mechanics that trajectory of the particle acted upon by such a force is conic. So uh, when a central force acts on the body, its path would be a conical shape. It is a kind of conic. So it could be parabola, hyperbola, or in a ellipse, like that. So the conic will be ellipse, parabola, hyperbola, depending on whether the initial energy. So it depends on the initial energy. So actually, how to remember this is eel. So for ellipse, eccentricity is less than 1. Eccentricity is less than 1. And for parabola, eccentricity equal to 1. And hyperbola, eccentricity is greater than 1 for hyperbola. So hyperbola, this is for parabola, this is for ellipse. So we might have studied in max. So based on that. So likewise, if energy is greater than 0, that is nothing but hyperbola. Less than 0 means that is nothing but ellipse. And equal to 0 means parabola. So in the present case, the initial energy of alpha particle is positive. So they are having certain, we can't say that the energy of alpha particle is minus 10 million electron volts, like that, but it is having certain energy that is which is positive. So the trajectory is a hyperbola with the scattering nucleus located at one of the foci. So just like for ellipse we have foci, that means two for this is one focus, this is another focus, like that. Hyperbola would be the case, would be the path followed by this particle, because energy is greater than 0, positive energy. Hence we assume the entire positive charge is concentrated on the point F. So that one we could see from this diagram. So this is that diagram. So here you could see this is the foci, this is the hyperbola. So this is the foci for this hyperbola. Actually the nucleus is here, the nucleus is located here. Only one nucleus it is located here. And alpha particle is trying to approach in this direction, but it gets deflected in as this direction. So this curved path is nothing but hyperbola with its foci here. That's why it is a falling hyperbolic path. So that is the meaning of this. So that one we would study why it is following such a path. So in this figure, the trajectory pa dash p dash of the alpha particle under the action of electrostatic repulsion force is shown. So trajectory pa dash p dash. So p a dash p dash, that is nothing but this is the trajectory. This is the path followed by the alpha particle, and the nucleus is located here. And the alpha particle is coming here. Let m and z dash e be the mass and charge of the alpha particle. So z dash is nothing but 2, as we have discussed in the starting. So plus 2e is the charge of the alpha particle, and it would be having some mass m. The nucleus is assumed to be infinitely heavy, and we are assuming that the nucleus is very very heavy compared to the alpha particle. So as the alpha particle approaches the nucleus F from again, the electrostatic effect is negligible, small, and when it is far away. So this is very important point. So when the alpha particle is far away, electrostatic repulsion force is negligible. In this case, its potential energy is negligible and entire energy is kinetic energy. So when the alpha particle is very far away, so that means especially here, The nucleus is located here. So actually the nucleus is located here, and the alpha particle is here in this direction. So when the alpha particle is here in this it is very far away from the nucleus. So you can see very far away from the nucleus. So that's why yeah, force acting on this alpha particle is negligible. So it won't be having, its potential energy is negligible, but its kinetic energy is very high. So here kinetic energy of the particle is very high. So we have just like if this is a ground, if you are standing at a great height, so we have high potential energy. If you are nearer to the ground surface, we have having less potential energy. So like that. Likewise, here also as the alpha particle is very far away, here it's electrostatic potential energy. This is gravitational potential energy, here electrostatic potential energy. So as it is far away from the nucleus, it is not experiencing any repulsive force, it is not opposing this nucleus. So its potential energy is negligible, but kinetic energy is high at this point. So that one they are saying. So kinetic energy, that is mv square by half mv square. So its initial velocity is v, where v is the initial velocity of the alpha particle. The path of the alpha particle at a greater distance. So at a greater distance is thus a straight line. So it is having a straight line path. So this is nothing but just like a straight line it is initially. So the alpha particle would be coming like this, almost like this only, because it is not experiencing any repulsive force. So it is nearly equal to a straight line coinciding with the asymptote QOR of the hyperbola. So this is the PA dash P dash, this is the hyperbola, and this asymptote they have mentioned QOR. So QOR, this is the asymptote tangent to that hyperbola. So this is the direction of that particle initially. So initially, so here you can see, so as alpha particle is going in this direction, so tangent to that is nothing but this asymptote. So its direction is this QOR. If we drop the perpendicular FG from the nucleus to this asymptotic line, then its length FP is the impact parameter. So this is the asymptote. Now we need to draw a perpendicular from the nucleus. So this is the nucleus. From here to here, asymptote is perpendicular distance is nothing but this B. So this is nothing but the impact parameter, that is closest distance of approach. So this one we should not get confused over here. So this, what is this impact parameter, that one we should understand. Suppose, so if this alpha particle is coming, actually it is coming in this direction. So if the nucleus would not exhibit any repulsive force on this alpha particle, so it would go in this direction, straight line like this. So it would go in this direction. So if it goes in this direction, then minimum distance of approach to the nucleus is nothing but this perpendicular distance B. So this is the minimum distance between alpha particle and the nucleus if it goes in this direction. But actually the alpha particle never goes in this direction. It is just an imagination. This asymptotic part is just an imagination, is our imagination. But so here initially at this point, the alpha particle experiences, so at this point this alpha particle experiences less repulsive force because it is at a greater distance from the nucleus. But as it comes here, as the alpha particle comes here, so it is at a lesser distance from the nucleus. As it is approaching, so distance between nucleus and the alpha particle decreases. So it experiences repulsive force. It starts experiencing repulsive force. That's why instead of going like this, it is changing its path. So slowly it is changing like this, instead of going like this, again like this. So it is just like the alpha particle is starting from here, So here it is somewhat deflecting. So the tangent at that particular point will show us. So so tangent at this point is like this, but tangent at this point is like this, but tangent at this point is like this. Tangent, just like for a circular path we would draw a tangent to show the direction of velocity. Here also if we draw the tangent, from clearly we could observe from these arrow marks, from these tangents, that the alpha particle is frequently changing its direction. Why it is changing its direction is because of the repulsive force. The nucleus is just opposing its, yeah, this alpha particle. It is just saying go away like that, because of its huge repulsive force. That's why the alpha particle is changing its direction frequently. That's why it has finally got this hyperbolic path, not this straight line path. If it is not, if the nucleus is not opposing that alpha particle, it could have gone in this straight line path, but no, it is repulsing it, it is opposing it. So that's why it is frequently changing. Finally it has gone into a hyperbolic path. So that's why we have got this kind of hyperbolic path. So if it had gone in this direction, the closest distance of approach is b, that is nothing but impact parameter. So if it has approached in some other direction like this, means like the likewise. So if it has approached in this direction, means the impact parameter would have been different one. If it has approached this direction, means impact parameter would have been this. So for the different directions of approach, there are different impact parameters, that also we'll see. So this is nothing but impact parameter. So as the alpha particle approaches the nucleus, its trajectory bends more and more away from the F due to increasing. So that is the thing I have explained now itself. It begins to move away from the nucleus A dash B along A dash B dash. So this is nothing but A dash B dash. So instead of going in this direction, it is choosing going back like this, nearly like this. It is coming and moving back with the asymptote r dash o q dash of the hyperbola. So for this path, for this a dash b dash, the tangent at this point, that is this asymptote. So r dash o q dash, that is the asymptote of the hyperbola. The angle ROQ dash between the two asymptotes is the angle of scattering, ROQ dash. So ROQ dash. So this is the angle. So Y means, so actually the alpha particle is coming in this direction. Initially it was coming in this direction. If we draw at the starting point, it is moving in this direction. We are seeing just a direction, not this path. So this is the incident direction, and after finally it is going in this direction. So it is going finally in this direction. So this is incident direction, and this is scattered direction. So angle, initially we have discussed the angle between incident direction and the scattered direction is nothing but angle of scattering. So that is nothing but this is the angle of scattering, that is ROQ dash. So this is the angle of scattering. So that's why R dash OQ dash. Sorry, ROQ dash. So that is nothing but angle of scattering. That means the particle was going in this direction initially, but it has gone to this direction. So this is nothing but scattering angle. Understanding this is very important of scattering. The two asymptotes are equally equivalent at an angle phi to the FF dash as this. So here we can see. So this is the asymptote and this is the axis of the parabola. So it is making an angle phi, and this asymptote is also making an angle of phi. So they are at equal angles. That one they are saying equally inclined. When the alpha particle the electrostatic force is maximum. So here when the alpha particle was here, the distance between nucleus and particle is more. But when it is here, the distance between alpha particle and the nucleus is less. So here it experiences huge repulsive force when compared to here, because the distance between the nucleus and the alpha particle has reduced a lot. So that one they are saying. Uh, Writing the least distance of approach fa dash q. So least distance of approach is nothing but this. This is the least distance of approach fa dash. This is the least distance of approach. It is nothing but q. Potential energy of alpha particle at a dash is, so this is very important. At a dash, potential energy of the particle, we know that potential energy is nothing but vq, v into q. V is nothing but 1 by 4 pi epsilon naught q by r. So here nucleus 1 by 4 pi epsilon naught charge of the nucleus Z e by q, and q is nothing but this alpha particle Z dash e. So that is nothing but this Z dash e square by 4 pi epsilon naught into q. So from this formula and from this formula we have got this. Here potential is developed because of the nucleus. So V, in the V we are having Ze, charge of the nucleus, and here particle which is experiencing force is alpha particle, so Z dash E. So likewise we are having that formula. And epsilon naught, for epsilon naught they have given this formula. So actually 1 by 4 pi epsilon naught is nothing but 9 into 10 to the power of 9. Its value is 9 into 10 to the power of 9. So if we send this epsilon naught that side and this 9 into 10 to the power of 9 into the denominator, we would have this. So 9 4s are 36, 1 by 36 pi 10 to the power of minus 9. So 1 by 36 pi 10 to the power of minus 9. Likewise they have given direct constant. So that is another thing. The velocity Vm of the alpha particle at a dash is minimum. So obviously at this point it is having most of the energy of the particle is kinetic energy. But at this point it is having both kinetic energy as well as potential energy. Like that. So just like if a body is here, if we drop a ball from this height, here entire energy is because of potential energy, and here kinetic energy plus potential energy, and finally kinetic energy, like that at this point. In the same fashion here also the same thing. So initially alpha particle is huge, having entire energy in the form of kinetic energy, and here it is kinetic energy plus potential energy, and potential energy is very very high here because more repulsion, more potential energy. So its kinetic energy at this point is half mv square. So the total energy is, so the total energy of the alpha particle, its kinetic energy of the particle is obviously half mv square, but initially its velocity was b, but now its velocity is vm. It has been reduced because of repulsive force. So total energy E is also kinetic energy plus potential energy, that is nothing but this. Simple. So equating this to initial energy of the alpha particle. So we know that energy is conserved. In case of central forces, energy is conserved. So initially the energy of the particle, that means the energy of the particle at this point is equal to the energy of the particle at this point. So that is the meaning of this. So initially the energy of the particle is half mv square, and now at this point, a dash point, it is this kinetic energy plus potential energy. And next thing is just need to, so this is the equation. Now we need to divide entire thing with half mv square. So here half mv square, if we divide, we would get 1. Here also half mv square means vm square by v square we would get. And here if we divide means, so here where actual confusion arises, here it is of the form a by b. Already b is dividing a. Now again we need to divide this entire thing with c. First a needs to be divided with b, then it needs to be divided by c. So it is just like c by 1, that is a by b into 1 by c. So like this we would write. So that's why we are having mv square. That is 4 pi epsilon naught into half mv square. 2 would get cancelled. So It is just like half mv square we need to write here. 2 ones are 2 twos are, so that's why 2 pi, and this mv square is remaining in the denominator, still remaining in the denominator. The meaning of it, this is, that's now I have explained. First a needs to be divided by b, then it needs to be, the result needs to be divided with c, so that's why it remains in the numerator, sorry, denominator. So don't, we need not get confusion here. So actually here we would get 1, here vm square by v square. So we, what we need to do is we need to send this term that side, so that's why we would have 1 minus, and here vm square by v square. If we divide and see, we would get based on that, so we can do that division easily. Again, the linear momentum of the alpha particle at a great distance is mv along the line qr. So this needs to be understood. So at a large distance, linear moment of the particle. So the particle was approaching in this direction initially. So its linear momentum is in this direction. And we know that angular momentum is r cross p. L is nothing but r cross p. All of them are vector. That means we could write it as momentum into perpendicular distance. So this is the momentum. It is going in this direction. Perpendicular distance from the nucleus is nothing but this impact parameter b. So because of this, so hence its initial linear angular momentum is mv into fg. So initially the velocity mass of the alpha particle we have considered m, and its velocity v, so mv, that is the momentum, into fg. Fg means, here you can see, this is fg, perpendicular distance, so don't get confused. So that is nothing but mv into b. In the similar fashion, at a dash the linear momentum of the particle is mvm. The velocity of the particle has been reduced to vm axis, so that its angular momentum at this point is mvm into fa dash. So when at this point the direction of velocity is in this direction, so that is vm dash, and perpendicular distance is nothing but this is the perpendicular distance. It depends on the path and curve and tangent at that point, so which is nothing but q, that is fa dash. So that's why mvm into fa dash. So force is nothing but mvr, angular momentum is nothing but mvr, momentum into perpendicular distance, r is nothing but perpendicular distance, so fa dash, so mvm into q. And we know that just as the energy is conserved in, say, central force, linear momentum is also conserved. So hence linear momentum, initial linear momentum must be equal to final momentum at linear momentum at some particular point. So equating these two equations, we would get this. So here mm will get cancelled, we would get this b by q is also vm by v. So b would be in this side, sending q this side, so b by q, and vm would be remaining on right hand side and sending this v that side, so vm by v. So like this we would get b by q is equal to v by m after cancelling out m. And next thing is, referring to figure 1.3, we know from the properties of hyperbola that, so from the properties of hyperbola they're saying, so just for so if we consider ellipse, so here it is a, and if this is a foci, the distance from center to the foci of the ellipse, so center to the foci is nothing but ae. Ellipse eccentricity is, it is less than 1, so hence it is ae. A multiplied with a fraction is less than a, so we would have ae in case of ellipse, the distance from center to the foci. Like the same manner here also, this is ae, of dash, that is of dash. So here this is the center of the hyperbola. and this is the foci. Center to the foci is nothing but AE. Here E is greater than 1. So like that. So actually here this is A, OA dash, and this is A into E, because in hyperbola eccentricity is greater than 1. That's why AE would be greater than A. So here you need to understand, here to here, so from this point to center to this point distance is A. Again from here to here it is AE, because eccentricity is greater than 1, like that, AE. So OF dash is nothing but AE. So that one they have represented here from the properties of hyperbola. OF dash is nothing but E into OA dash. OA dash is nothing but AE. And Q is nothing but FA dash, that is OF into OA dash. That is, so this is nothing but Q, that is nothing but OF into OA dash. OF is nothing but AE, OA dash is nothing but A. So AE plus A. So that is the thing. It is OF plus OA dash, and we know that OA dash is nothing but OF by E. So OF by, this could be written as OF by E. Again if we take OF common, we would have 1 by 1 plus 1 by E, like this. So this is the formula we would get finally. So don't get confused, it is based on the properties of hyperbola, and another based on another property, 1 by E is nothing but cos phi. So on substituting these values, so 1 by E in the place of 1 by E cos phi, so it is replaced with cos phi. This is from the properties of the hyperbola. And next thing is sin phi. We need to find sin phi. What is sin phi? So from this figure, so if this is phi, this angle is phi, this angle is also a phi, because it looks symmetric. So this is also a phi. So sin phi is nothing but opposite side. This is the opposite side by hypotenuse, that is FG by OF. So hence we are having FG by OF sin phi. And so in the place of OF we could write OF, if we send this OF to that side it would multiply, and OF and sin phi to this side it would get divided. So OF is nothing but FG by sin phi. So OF FG by sin phi. So in the place of OF it is replaced with FG by sin phi, and 1 plus cos phi would remain as usual. And here FG is nothing but B, that is impact parameter FG. So impact parameter, and impact parameter 1 plus cos phi sin phi. And next thing is, so we know that B by Q. So if we send this Q to that side, B by Q it would become, and this 1 plus cos phi divided by sin phi to that side, it was sin phi would become numerator and 1 plus cos phi would become denominator. So we would get this. So B by Q is nothing but sin phi by 1 plus cos phi, and we already know that B by Q is nothing but V by M, Vm by V from this equation. So B by Q is nothing but Vm by V. So then from equation 1.2225 we have, so 1.22 means 22. So this is the equation. So Vm square by V square is there here in this equation. Here also Vm by V is there. So here right hand side would remain as usual. So from this right hand side as usual, 1 minus zz dash e square, 1 minus zz dash e square as usual. But in the place of Vm square by V square, so Vm square by V square, so that is nothing but this. Vm by V is nothing but sin phi by 1 plus cos phi. Whole square is nothing but sin square by 1 plus cos phi whole square. So that one we are having. And again here just a simple calculation. Sin square phi is could be written as 1 minus cos square phi. That means sin square theta plus cos square theta is nothing but 1. So sin square theta is nothing but 1 minus cos square theta. 1 minus cos square phi could be written as 1 minus cos phi into 1 plus cos phi. That is a plus b into a minus b is nothing but, so cos phi it is. A plus b into a minus b is nothing but a square minus b square. So numerator would be this. In denominator we are having 1 plus cos phi whole square. So 1 plus cos phi and another 1 plus cos phi would get cancelled, and 1 minus cos phi and 1 plus cos phi would be remaining. So that is the calculation. So finally this term is equal to this one. So here we can see, and substituting for q from 1.25. So q, if we send this q that side, so b into 1 plus cos phi divided by sin phi. So b into 1 plus cos phi divided by sin phi. So here q is there in the place of q, b into 1 plus cos phi divided by sin phi. That one we need to place. So that one we have placed here. And next thing is calculation, a simple calculation. 1 minus this term has to be sent to that side. So here actually here if we send this one to this side, that one calculation has been given here, so no matter. So 1 minus this term if we do, or else here only you can see. So it is of the form some a by b minus 1, that is nothing but a minus a by b minus b by b, like that, a minus b by b. So 1 minus cos phi minus of 1 plus cos phi, if we do from here you can see. So 1 minus cos phi minus 1 minus cos phi, minus 1 plus 1 would get cancelled, minus 2 cos phi by 1 plus cos phi we would get. That is if we do this term minus 1, but here we have to do 1 minus this term. So that's why 2 cos phi is remaining divided by 1 plus cos phi. Here 1 plus cos phi, in here also 1 plus cos phi would get cancelled. So what would remain is this sin phi. So here in the inside, if you do understand the calculation here, you could get it easily. So finally what we would have is, we need to send this b to that side. What we want is a impact parameter. So this 2 cos phi needs to be sent to this side. So 2 into 2, that is nothing but 4 pi epsilon naught mv square, and sin phi by cos phi is nothing but tan phi. So b is nothing but this. This is the formula for the impact parameter. And from the diagram, so here you could see this is phi. This entire thing is theta, angle of scattering. So then this would be theta by 2. So this phi plus theta by 2 is nothing but 90 degrees. So that's why here we are having phi plus theta by 2 is also pi by 2. Pi by 2 is nothing but 90 degrees. So phi is nothing but pi by 2 minus theta by 2. So in the place of phi, we need to replace it with 90 minus theta by 2. So tan of 90 minus theta by 2 is nothing but cot theta by 2. Tan of 90 minus theta is nothing but cot theta. So from that we are having this. So finally this is the impact parameter. So this shows, equation 1.27 shows that shows has the impact parameter becomes. So this is the formula for the impact parameter. As the impact parameter becomes smaller, the angle of scattering increases. So here this one we need to understand. So as the angle theta increases, what happens is tan theta increases. But cot theta is the inverse of tan theta. So cot theta by 2 decreases. That means b is directly proportional to cot theta by 2. So b also decreases. So finally what we are getting is, as the angle of scattering increases, impact parameter decreases. So here you can see the impact parameter becomes smaller as the angle of scattering increases. So that is the meaning of this formula. This dependence on theta is shown schematically. So here you can see. So here the angle of scattering is less, but here the angle of scattering is more. This let me indicate it. So here the angle of scattering is more. So this is the angle of scattering. So at the blue mark, the angle of scattering is less, but at the red mark, angle of scattering is more, because the impact parameter is less. For the red one, impact parameter is less. That means the closest distance of approach is less. But for the blue one, the closest distance of approach. So if this is the nucleus, the red one is here and the blue one is here. So closest distance of approach is less for the red one and more for the blue one. So hence blue one is getting less scattered and red one is getting more scattered. So that one you can see shows that as the impact parameter b becomes smaller. So as the impact parameter b becomes smaller, the angle of scattering theta increases. So smaller is the distance smaller is the close distance of approach, more is the angle of scattering. So this is very important result. Product was the scattering nuclei. We have different effect, so that one I have explained already. If the alpha particle approaches is in different direction, different asymptotes, different impact parameters. So if we draw two infinite coaxial cylinders of radii b and b plus, they having their axis parallel to the incident direction, less then all alpha particles with their same between these two cylinders will be scattered between angle theta and theta minus theta. So we are just drawing a cylinders. So this is a cylinder of radius b and this is a cylinder of radius b plus db. So all alpha particles falling within this impact parameter would be scattered in theta minus theta dash. So let me explain it with the help of a diagram. So here, so one way of approach. This is the alpha particles whose impact parameter is b. So now let us suppose another alpha particles whose impact parameter is b plus db, somewhat increased. That means this. So its corresponding going direction would be this, and for the blue line it would be this. Sorry. So here we need to understand that this blue line's impact parameter is b and this red line's impact parameter is b plus db. So here you can see angle between two blue lines is theta and the angle between two red lines is getting reduced, that is theta minus d theta. So as the impact parameter increases, scattering angle of scattering decreases. So if it is alpha particle is going very far away from the nucleus, it gets less scattered. So that one they are saying here we need to consider a cylinder of radius b. So with the axis, the nucleus remaining in the axis. So here we need to consider a cylinder. So like this one cylinder we need to consider. This is one cylinder, this is another cylinder. So that same thing they are considering here. So such that b and b plus db are the impact parameters. So the theta minus d theta. So that is the thing, nothing much. And the two cylinders area between these two cylinders, that means we could say overall it has two circles. So let us suppose so here if this is a circle of radius b, its radius is b, and this another circle of radius b plus db. So if I remove the smaller circle from this bigger circle, what areas? So that is nothing but area of the bigger circle is pi r square, that is pi into b plus db whole square minus pi into b square. So that resultant area is nothing but area of this annulus. So that one they are saying. So these are nothing but alpha particles moving in between b and b plus dp. So this if we solve we would get two terms. So this is a plus b whole square, a square plus b square plus 2ab. So but we are neglecting db whole square term because db is very small. So 2 pi db. From that formula also we could get this, or else if we think creatively, so this is circle of radius b. So 2 pi b into, so it is outer layer is of width db. So 2 pi b into db. So we would get the thickness of this ring like shape. So like that also we can think. So 2 pi b db, that is the area of the annulus between them. So that the particles incident on this annulus give in the given time interval. So n is number of alpha particles incident per unit area. So in the unit area, this many alpha particles are incident. But here the area between b and b plus db is 2 pi b db. So if we multiply this with 2 pi b db, so here you can see n into 2 pi b db, we would get the alpha particles falling in this much area. N is the alpha particles falling in unit area, but we require for this much area, so that's why we just need to multiply them both. Where n is the number of incident particles per unit area, we get scattered between, and that is alpha particles scattered between theta and d minus d theta. So finally n would remain as usual. 2 pi would remain as usual. 2 into b is nothing but b db we need to find out. So b is nothing but this, just need to place here z dash e mb square cot theta by 2. And if we differentiate this db, because in the formula it is 2 pi b db, so if we take db differentiating on both sides, if we do db as this is a constant, so it would remain as usual. So differentiation of cot theta is nothing but minus cosecant square theta. So here minus cosecant square theta by 2, again if we differentiate theta by 2, 1 by 2 would be coming out, 1 by 2 t theta. So that 1 by 2 into this 2 pi, 2 would get cancelled, pi would be remaining, and minus we are getting because differentiation of cot theta is minus cosecant square theta. And next thing is uh, minus cosecant square theta would be having, this is nothing but cot theta. Cot theta by 2 would be written as cos theta by 2 sin theta by 2. 1 by sin theta by 2 is nothing but cosecant theta by 2. Hence we are having cosecant cube theta. Already one cosecant square theta by 2, another one 1 by sin theta. So that is nothing but another cosecant theta by 2 into cos theta by 2. So this is the thing you were having finally n in the place of n. So dn is nothing but this, all these alpha particles scattered into solid angle. So solid angle is just like, so for a circle angle is two dimensional, circle is two dimensional. So if we consider the case of sphere which is three dimensional, so three dimensional angle is nothing but solid angle in three dimension, just like a cone. In cone, if you consider the angle of the cone is nothing but three dimensional, so that is nothing but some sort of solid angle type. So formula for solid angle is 2 pi sin theta d theta. So here you can see theta angle varies from 0 to pi. So if you do integration of sin theta minus cos theta, so cos phi minus cos 0, cos phi minus 1 minus 1. So entire solid angle is nothing but 4 pi. So that is this formula. Need to remember this formula. And we know that sin 2 to theta is nothing but 2 sin theta into cos theta. Here also same thing. Sin theta is nothing but 2 sin theta by 2 cos theta by 2. 2 2s are 4. So that's why 4 pi d theta. So this is the formula for d omega. That is solid angle. Thus the number scattered per unit solid angle. This is the alpha particles scattered in this annulus. That is theta and theta minus d theta. So for this much solid angle, so dn by d omega for unit solid angle. So we just need to divide these both equations. So if we divide, finally if you do calculations, you would get this cos theta by 2 would get cancel d theta, another 1 by sin theta by 2 cosecant power 4 you would get. So likewise, and pi would get cancelled. So likewise so likewise if we do calculations, we would get this finally, this term. And another important thing is, in the place of z dash we need to replace it with 2. because plus 2e is the charge of the alpha particles. So 2 square is nothing but 4. So that 4 and this 4 would get cancelled. So the 4 here, from here 2 square 4 and this 4 would get cancelled. Finally we would have this formula. So this is the formula. The negative sign appearing has been dropped because here this negative sign tells us that as the impact parameter increases, scattering angle decreases. So if one increases, the other term decreases, we would definitely have minus sign. So that is removed. So this is the above deduction. So this is the theory, you can read it. So if dn by n, so this many out of n alpha particles, dn alpha particles are scattered. So that is nothing but probability. So that one they are saying, that is indicated with d omega. So this n, if we send to this side, dn by n we would have, that is nothing but d sigma by d omega. So this entire thing would remain as usual. So that is just like out of one alpha particle falling, so how much it is, what is the chances of its being getting deflected. So that is nothing but probability. That one they are saying, that is the explanation of this theory. So this is finally we have got Rutherford's scattering formula. So this is the Rutherford's scattering formula finally, by sending this n to that side, probability. And this and again what they are saying is, this would have the dimensions of the area, that one they are saying. So Rutherford's scattering formula. So because this is having the dimensions of energy and length, so actually energy and length, so that is we know that force is nothing but 1 by 4 pi epsilon naught q2 by r square, like that. 1 by k, if we see, if we send this r square to that side, force into r square, force into displacement is energy, energy into length. So that's why here it is given as, this is having the dimensions of energy into length, and this is the having the dimensions of energy. So energy into length divided by energy, that is nothing but length, that is nothing but length square. So this is having the dimensions of length square, that is area. Hence it is indicated with cross section. Hence we would say differential cross scattering cross section. Cross section means area, because it is having the dimensions of area. So that is the meaning of this. And next thing is delta, if n alpha particles are incident on the foil, delta n is scattered into solid angle delta omega. So the number of particles scattered would be directly proportional to number of particles present falling per unit area. More is the number of alpha particles in unit area, more is the scattering. If there are 100 scattering alpha particles in a given area, more would be the scattering. If there are 10 alpha particles, scattering would be less, like that. So delta n is directly proportional to n, as well as solid angle. So how more is the solid angle, more is the scattering, and into n1. n1 is nuclei present per unit area. More is the nuclei, more are the scatterers. So more is the scattering. More are the scattering centers, more would be the scattering. More dense is the atom, is the nuclei. So more would be scattering them. So that is n1. So if we remove proportionality symbol, we will get constant of proportionality, that is d sigma by d omega. So this d omega would get cancelled, n into n1. So like that. So actually it would be a three-dimensional. The foil which we use, it won't be that much thick. So it would be having certain thickness. So we need to consider thickness also. So here you can see n1 is nothing but n into t. N is number of scattering nuclei per unit volume. In unit volume, how much nuclei is present into thickness of that foil gives us how many nuclei are present in a given area. So they also matters in the process of scattering. So this is nothing but foil. So alpha particles falling on this foil. So if we substitute in the place of n1, nd and everything, so we would have this formula. So n d sigma, if we d sigma into d omega, if we substitute in the place of d sigma this formula, so finally we would have this formula. And next thing is, so here they are saying us to draw a cones So it is a three-dimensional. So solid angle is conical form. So we need to draw cones for different scattering angles. One is for theta, another one is for theta plus d theta. So if we draw the cone, so this cone, this is one cone. So here if we see sine theta is nothing but opposite side by hypotenuse. So this side by r. So r into sine theta is nothing but this height. And next thing is, here we know that length of the arc for a circle, if it's of radius r and angle is theta, theta is equals to l by r, theta is equals to l by r, like that. R theta, l is nothing but r theta. So here also r into delta theta, that is the arc length. So here we are having, actually here we are having circle of radius r sine theta, and here r delta theta. So this area between these two cones is nothing but 2 pi r. Radius of that circle is r sine theta, inner circle, and r delta theta, that is angle between these two cones, areas, cones, or these two rings of the cones, r delta theta, that is length of the arc. So from this 2 pi r square sine theta delta theta, r square delta theta. So this is the thing. So alpha particles scatter into solid angle delta theta scattering pass through this strip. So all these alpha particles which are getting scattered at an angle theta and d theta, they all pass through this strip, this entire circular strip. So that is the angle of this strip. We need to consider the conical form. If we consider conical form, so you would get a ring-like structure, that is this strip. Hence the number scattered falling per unit area of the strip. This is, so if you want to get for unit area of the strip, this is for the entire area of the strip, delta n. For unit area of the strip, delta n by delta s. So if we just divide with this equation with this, we would get finally this. So this is the thing we would get. Here r square, this is delta omega, they have represented. This so formula for omega 2 pi sine theta d theta. So here also 2 pi sine theta d theta is replaced with delta omega. So likewise we have finally got this formula. This is for unit area of the strip. So actually the strip would be of this much area, but we want for the unit area of the strip between the two cones. So this is the thing. Actually the formula ends here. So this is until here, this is the actual formula, Rutherford scattering formula. So this is in detail we are studying its about its dimensions and everything for unit area of the strip in the three-dimensional surface. So this is the concept of Rutherford's scattering formula. This is the entire concept, and this is the Rutherford scattering formula. This is the complete theory and notes. So this is the explanation. So thank you.